What is metal? So metal is basically what we call a substance that is composed of one or more metallic element. Okay, we learned about element before in the periodic table. They are like a table of elements. So if you look at the periodic table itself, you can see what we call, if you click at the metal, almost like 80% of the periodic table is made from metal, is composed of metal. So we know metal is ubiquitous in periodic table itself. Okay, so this is metal from the lithium, beryllium, sodium, magnesium, potassium until this bismuth, lead, polonium and so on lah. So this is metal, and this is what is between metal and non-metal, and this is non-metal. We have learned this in the periodic table previously. So coming back, what is the definition of metal? Metal is a substance composed of one or more metallic element. Example, so I give example there: iron, aluminium, copper, gold, silver, etc. And often also combined with non-metallic element, for example, carbon, nitrogen, oxygen, in relatively small amount. Okay, so this is generic definition of metal. Generic definition of metal. They are, when you are combine different metallic element together, there are specific term for that. We call it alloy. So metal alloy refer to a metallic substance that is composed of two or more element. Okay, composed of two or more element. One of it must be metal lah. One of it must be metal, and the most important part is this: and still retain all the properties of metal in resulting material lah. Okay, I repeat, metal alloy refer to metallic substance that is composed of two or more element, in bracket at least one must be metal, and still retain all the properties of metal in resulting material. The important part here, the important sentence here is the last sentence: still retain all properties of metal in resulting material. Why I say it's important? Because if let's say I show you, let's say I show you this thing. Okay, let's say this is 3D printing filament. Okay, we will learn about 3D printing later on for your project. But for the time being, 3D printing is just basically a process that you take what we call a filament, a plastic filament, put in the machine, and machine make what we call a design, 3D design based on your what you draw lah. So for example, this is what you can get from the 3D printing lah. So you draw this in the software, and then you use a filament. Plastic filament, put in the machine will hit the filament, and then filament will coming out, and then it will sort of like move here and there and make this object lah. So the main thing, the raw material for 3D printing, normal 3D printing, is filament. So this filament, as you can see here, is basically, they call it what? The best 3D printer metal filament. Okay, but this is not actually a metal. It's not 100% metal. Okay, this is metal plus something, metal plus plastic. Because remember, in order to make 3D printing possible, you need to melt the filament in order to convert it into a shape like this. Okay, you need to melt first. Melt the filament in the, what we call in the machine itself, in order to make this object. If this is metal, you need to you can melt metal, but you need very high temperature. If you look, let's say I put here, let's say I duplicate here, 3D printing, let's say 3D printing, let's say I put here, delete. Okay, so if you look at 3D printing like this, a 3D printing like this. This part is what we call the extruder part. You have a nozzle here, and this is where the heating start. Okay, so the filament will be fit into the feeder. So for example here, the filament will be fit into the feeder here, into the extruder here, and this is where the filament will be melted, and then you get something else at the bottom. So when you want to melt a metal, you can melt the metal. Metal can be melted, but you need very high temperature. You need around like 1000 plus Celsius in order to melt temperature. But common 3D printing here, for example, the common 3D printing, the maximum it can go is around 300 Celsius. Okay, 300 Celsius. That is the common commercial, not commercial, I mean the domestic 3D printer that you can see all around you nowadays. the maximum temperature it can melt here is 300 Celsius. Not enough to melt a metal. Okay, so now the question now, if this is the best 3D printer metal filament whatever here, how they melt the metal itself? Because the metal cannot be melted at 300 Celsius. So that's just to say that this is not metal, pure metal. It's not like, let's say this copper. It's not copper. It's not copper filament 100%. It's basically copper plus some plastic lah. So that's, we doesn't say that's alloy, because in this case, if you look here in the filament, so for example, let's say I draw the filament like that. So this is the filament. So this filament, if you see from this filament, okay, let's say the metal is in the red here, inside here, the red. So what happened in that metal? So let me put here. So what actually inside that is basically like this. Let me draw in the green. In the green. So let's say this, and then you have a metal particle inside. Okay. So this is what we call metric. The green one here, we call it metric. This maybe we can call it filler lah, filler. Okay. In this case, when you want to make a metal filament, they call it metal filament. I put in the bracket here because it's not pure metal. It's not pure metal. It's basically a plastic plus the metal. So the metric here is basically the plastic lah, the plastic, the polymer lah. Normally the polymer, and the filler here is a metal. Okay. So when you see what we call this 3D printing filament with the metal, they call it metal filament. There only a very few percentage, very low percentage of the metal inside the metric, inside the what we call the filament itself. So the rest of the what we call the rest of this, the metric, is basically a plastic. Basically a plastic. Normally they use PLA lah, polylactic acid. Here we don't call this thing, the entire thing, we don't call it as alloy. We don't call it alloy. Because why? Because why we don't call this alloy, even though there are metal inside that, is because it doesn't, remember the definition of alloy. Remember this thing, the last part here. Retain all the properties of metal in resulting material. Okay. So when you make a sort of like this filament, it's quite difficult for me to go here and there. So if you make this filament, the majority, the bulk of it is basically plastic, and only a few percent is a metal. So we don't call that alloy. We call that composite. We call this thing, rather than we call alloy, we call that as a metal polymer. Polymeric composite lah, composite reinforced with metal. Okay, this is not alloy. We don't call that alloy. Okay, so this we just call it composite lah, a composite, because you need to sort of like differentiate what is alloy, what is composite, because composite also, the definition is a mixture of two different things. Alloy also a mixture of something, two different things, right? But just in alloy, the most important one element must be metal, and that's one thing. And then the second thing, it must retain, the product must retain metal, properties of metal. Okay, let me talk about this. What does it mean by must retain the properties of metal? In order to know what does it mean, we need to know what is properties of metal, the generic properties of metal. Okay, so this is example of this what we call the metal lah. So this gold, the first one is gold. So this is pure metal. Some metal is priced due to in its pure form. So this is gold in its pure form. But most metal that you can see around you, in the daily life is not pure metal. It's normally alloy. For example, this drink cans. even though you know it's made of aluminium, it's not 100% aluminium. They add something, so they call it alloy. Okay, and also steel here. This is steel, the one that you make use for the construction or whatever. This is not a pure what we call pure element, because the name itself steel is basically a combination of what we call the iron and also the carbon. We will talk about steel later on, but just to show you that whatever you see about metal in your daily life, normally it's metal alloy. It's not a pure metal. Okay, very rare you use a pure metal. Normally a pure metal like people sort of like you encounter in daily life, like a gold, like a silver, that is very pricey lah normally, and also they are not much use lah. For example, you cannot use gold. When I say not much use here, it means that doesn't have much use in engineering sense lah. For example, let's say you want to make a building, you don't make it from the pure gold, because gold is very soft. Okay, gold is very soft. You use steel because steel is harder than gold. So yeah, that's the thing. That's the reason why you don't see pure metal in your daily life. Because in daily life, especially when things require a strength, the pure metal normally combine with other stuff and make an alloy. So we need to understand here the last part here. Still retain all the properties of metal in resulting material. What does it mean by still retain all properties? So we need to know what is properties of metal. So what is the properties of metal? The first properties of metal is a good electrical conductor. The reason for this is because in metal, the atom is connected with the metallic bond. In the metallic bond, the electron is free. Okay, so electric is basically the movement of electrons, sort of like that. So because of the delocalized electron or free electron, then metal can serve as a good electrical conductor. Okay, okay, so that is the first properties of metal. So in order, when people say what is the property of metal, the first thing that comes to your mind is it must be able to conduct electricity. Why? Because they are free electron. So the free electron will help in electrical current. Okay, and then also another property of metal is have good heat conductor same idea with the electrical, because of the free electron. The another properties of metal is ductile. Ductile here meaning that it easy to form. It's malleable. For example, it's malleable. For example, let's say you can see the paper clip there. You can bend the paper clip many times without it breaking. If this paper clip made from the wood, then it will snap. Okay, it will snap. But this paper clip made from metal. Okay, and the metal, one of the properties is ductility. Okay. Okay, even if you, let's say you test a metal, let's say you have, like, for example, like this, the what we call the metal rod. If you try to pull the metal rod, it will not just break like that. It will have something. It will neck. This is what we call necking. Necking. We call it necking. It's difficult because I use only one hand. Wait. So when you have metal, ductility. So this under ductility. Ductility. If you have like what we call the metal specimen here, metal specimen, and then if you try to pull, okay, to pull it away, so this is basically tensile. Tensile is basically you pulling out . So what will happen for the metal? It will necking. It will not just break like that. It will experience something like this. Okay, so it will experience what we call necking. So let me put here, and then let me draw something like this, something like this, and then it will sort of like it will sort of like wait. Okay, it will have this what we call this necking. We call it necking. Necking. Okay, so it will have necking. So that's why when you see this thing, you can see the necking happen. If this is, let's say, polymer, if this if this is ceramic, let's say you have like bricks, this brick, normally your house is made from bricks. If you try to pull it, it will not have these properties. It will just fracture like this, like explosively. It's just brittle fracture. So this is what we call ductile fracture. This thing, what you see here, the necking here is telltale of a ductile fracture. It will break, but it doesn't break just sort of like just like that. It will have sort of elongation, not elongation. It's more like necking lah. That's why it look like a neck there. Okay, so that's what we call ductility, the ability to deform upon stress. Ductility means the ability to deform, under load, under stress without breaking lah. So that's what does it mean ductility. That's why you can sort of like you can bend the paper clip, paper clip many times because of that lah. Okay. So now the reason why metal is ductile, you can see the reason. Nah, apa ni? Ada. Ada. Okay, the reason why the reason why metal ductile is because of their internal what we call internal structure. If you ever take the metal and you put under the microscope, good microscope, you will see something like this. Okay, something like this. This is green. This is green. So I will show you. Okay, normally you know metal, inside metal we learn in the crystallography, the atom is sort of like what we call sort of like arranged in order like this, right? In order like this. Okay, so this is in the perfect world. The all the atom arranged very what we call they are very ordered lah, very ordered. That's in the crystal. But in normal metal, it doesn't like this. It's sort of like it have something like this. It just something like this. Hey. Apa? Jap. Nanti dulu. Okay, so you can see that image there. You can see the circle thing is basically the what we call the atom lah, the atom. So you so basically, if you look there, if this is perfect crystal, you will see all the atom aligned in one sort of like one row like that. But here you can see they are sort of like, say this part here, you can see the atom is like this, and then suddenly the atom they sort of like a dislocation. We call it dislocation. Dislocation. So they are sort of like defect. We call it defect. Defect in crystal. We call this is defect in crystal. Defect in crystal. Okay, that's basically defect in crystal. Defect in crystal. So when we heard the word defect, normally we think something bad. But for metal, defect or dislocation is the good thing. Okay, because of this defect, the metal, the what we call the atom can move. For example, when you bend, the dislocation will be moved. Okay, when you bend a paper clip, what happen is that the dislocation move. Okay, so the dislocation, when dislocation move, the atom also move somehow. So, but it doesn't break. It move. Dislocation move. Dislocation here doesn't mean there are no atom. There are no atom. No, it doesn't mean. It's just like they are extra. For example, like this. Let's say this is what we call. Let's say they are. So for example, let's say this normal is like this. Normal like this. But if you have dislocation, so for example here, let's say like this. They are so for example extra. They are still atom in the lattice, but then the atom is not aligned sort of like perfectly. So they are extra atom or they are less atom. So because of the extra atom, the green here. So because of this green atom here, the otherwise perfect layer like this, the otherwise perfect layer like this become distorted here. Okay, become distorted because of this the appearance of the what we call an extra atom. Okay, so it doesn't mean that dislocation mean there are no bond. They are bond. It's just there are extra atom or there are less atom, making the lattice not so perfect. So that's what does mean dislocation. When you bend a paper clip, what will happen? This thing will move lah. The dislocation will move. So this part will move. This part will move, and when this move, whatever this move, it also move the atom lah. Okay, because dislocation is part of the atom itself lah. It's just the atom arranged is not in what we call in a perfect row, perfect column like that. So like that. So if you look here, so this is what you see under the microscope. You can see there are like a grain, and then there are boundaries. The boundaries there is the dislocation. The boundaries there is the dislocation. So if you see under the microscope, you can see something like this, something like this. Okay. So if the atom is sort of like this, is the blue one. So you can see. So like that. Okay. So imagine the blue one is the arrangement of the atom lah. Okay, arrangement of the atom. But the arrangement is sort of like hampered by this dislocation lah. I mean, it's sort of like distorted by the dislocation. We still say that the metal is crystalline. It doesn't mean this not crystalline, because if you look here, if you look this one, the one that I sort of like highlight with the yellow highlighter here, that is still what we call still crystal, because you see the atom have the one direction. It goes to one direction. It's just this what we call metal is type what we call polycrystalline material, because you can see there they are crystal, because you see the definition of crystal is basically when the atom is arranged in what we call atom, ion or molecule is ordered, is arranged in orderly manner, mean that periodic, over the large atomic distance. Okay, so this, even though you see this is not so large atomic distance, but at the microscopic level, this might be like 1,000 billion of the atom there. So we consider that as a what we call crystal lah, crystal. Okay, so metal is type of polycrystalline material because of this. So this, the one in this one, we call it grain boundary. Grain boundary, or in other words, dislocation lah. Okay, so this is what make metal ductile. Okay, what make metal ductile? If the metal, okay, let's say if the metal just like this, just one single crystal, then it will not be ductile. And we see before in the previous class when we talk about the quartz. Quartz is a single crystal. So you can see quartz, if you try to break it, it will just snap like that. It will not malleable, because it's just a single crystal. You break everything, but there are no dislocation there. But in metal there are dislocation, and this dislocation is what responsible for ductility of the metal. So that is the what we call the third properties of metal lah. The third properties of metal. And then metal is opaque. Another property of metal is opaque. I mean, there are no metal that is transparent. I mean, of course there are people will claim that there are metal that is transparent, but they do something else to the metal lah. But in general, metal is opaque. Okay? Metal is opaque. The reason for this is because of the metallic bonding inside the metal itself. You know, in metallic bonding, the electron is free. So when the light shines to the metal, this free electron will sort of like absorb the light. Okay, absorb the light and sometimes reflected back. Okay, so that's why metal is opaque. So the light cannot go through because the electron that moving around the metal is sort of like absorb the light itself lah. Okay, sometimes when you sort of like polish the metal, the light that is absorbed sometimes will be reflected back. Okay, some light will be reflected back. So if you polish the metal, you will get this shiny or lustrous appearance. So this is properties of the metal lah. So and then some metal have magnetic properties lah. For example, iron, ferrum is iron, cobalt and nickel. If you have ferrum, cobalt and nickel, more often than not, they are not more often than not. It depends lah. It depends. Because we don't talk about magnetic properties this semester, but it's okay. But just to tell you that if let's say the metal contain ferrum, cobalt or nickel, they have the ability to become magnetic. Okay, you have ability to become magnetic, but not all metal is magnetic. For example, gold is not magnetic. Gold, silver is not magnetic. Okay, so this is properties of metal. Okay, properties of metal. When people say what is metal, what is properties of metal, this is 6 properties of metal lah, the most common properties of metal lah. Okay, so if we coming back to the previous slide, we said metal alloy refer to metallic substance that is composed of 2 or more elements and still retain all the properties of metal in resulting material. So if we look back to this, if you look back to this metal sort of metal quote unquote filament, this metal filament, if you ever sort of like encounter play with this stuff, you will see when you try to bend it, it will snap. Okay, you will snap. It will not be like a paper clip. You take a filament and then you take a filament. Tidur ni. Tidur ni. If you take the filament like this, that filament, and then you try to bend it, it will snap. So that is not the properties of metal. So that's why we don't call this alloy. This thing, okay, this thing, what is this thing? Okay, this thing, if you try to snap it, what will happen? It become like this. If you try to sort of like bend the filament, what will happen? It will snap like that. It just snap like that. It just snap like that. You snap. So that's just a telltale sign that this is not really alloy. This is more like a composite. It's like polymeric composite. Okay. So alloy, it must retain the metallic properties lah. The product must retain all the properties of metal in resulting material. That's part of the important part lah, to differentiate between alloy and also a composite that have a metal inside that. Okay, so that is metal, alloy, properties of metal, and then what else we want to learn. Okay, so we know that most of the metal that you see in your daily life is not pure metal but rather alloy. So we will go a little bit deeper, not deeper, I mean we will dig further into metal alloy lah, because this is more useful than the talking about metal, pure metal lah. Because pure metal you learn during the periodic table lah, element in the periodic table. So what you see nowadays is most in your daily life is basically metal alloy. Okay, so alloy is basically an art of preventing movement of dislocation. The idea of alloy is basically like this. Let's say you have like what we call, let's say I have this atom of iron. Let's say I have this iron. Okay, let's say I have this iron. Okay, let's say this iron. Okay, by itself in a pure form, iron is soft. Okay, iron is soft in a pure form. Okay, so because this thing will slide, and here this what we call this lattice, the atomic lattice will slide here and there. That's why iron is soft. So when you make alloy, what does it mean by making alloy? Is that you add impurities. You add impurities into metal lah. So for example, let's say you have this carbon. Let's say you have carbon, and then you put this carbon inside this. You just add this carbon as impurities inside this thing. You don't put a lot, you just put a little bit, and these impurities enough to sort of like arrest the movement of the sliding of the atoms lah. Okay, so it's like you sort of like sendal, apa dalam bahasa Melayu we call it sendal something. You put your your feet on the door to prevent the door from the close. So it's sort of like that. You sort of like interrupt the movement of the door by putting your feet. So that's more or less like this lah. Alloy is basically you put the what we call the impurities. In this case, whatever impurities. For example, in this case, let's say we put carbon here. So this carbon sort of like prevent the movement of the iron atoms during the what we call bending or whatever. So when you do that, when you put carbon inside iron, what will make this will make iron stronger lah. Iron stronger lah. Not stronger. I mean that it make iron stronger lah in term of because when something is soft, we don't call it strong lah. So if you want to use iron as what we call structural material, for example, you want to make like a bridge, where the car can go. So you don't want, let's say you have bridge, and then you have the car on top of that. If you use the pure iron, then the pure iron will just sort of like become so ductile, become so soft to the point that the bridge will collapse. So when you put the impurities in terms of carbon, this ductility is sort of like being hampered. So then this whatever product here, we call it steel, is become stronger, can resist very ductile properties lah. Ductility is important, but sometimes we don't want too ductile. Okay, if you want to make a structural material, you don't want that material too ductile. We want some ductility, but we don't want very ductile, because if very ductile, then it just collapse lah. The structure will just collapse. So that is the purpose of alloy. Normally we make alloy in order to increase the what we call the strength of the material of the metal. So the key principle of alloy is basically it arrests the dislocation in metallic lattice lah, okay. They sort of like arrest or interrupt the dislocation from moving in metallic lattice. Okay, so that is the idea of alloy. Okay, so alloy is an art of preventing the movement of dislocation. Okay, so the alloy can be divided into two big parts. The first is non-ferrous, and the second is ferrous. Okay, usually under alloy you can classify things into big class lah. First is non-ferrous, meaning that the alloy that does not contain ferrum or iron lah. Ferrum is iron lah, does not contain iron. Example is copper alloy. Okay, example is copper alloy. Okay, example. So this, when you see this, what we call this, my cursor here, if you see this is like copper. In electrical wire, they use copper. Okay, you know the copper here is very soft, right? You can feel it. You get the idea how soft the copper is. So this is a brass. Okay, this the pipe here, the brass is tembaga lah, tembaga. Okay, in Malay we call it tembaga. So this is copper alloy. Okay, brass is basically the combination of copper and also zinc. Okay, copper and zinc. So if I may here, so brass, so brass is basically copper plus zinc. Okay, and then you have another one is bronze. Bronze is basically gangsa. Brass is tembaga. Brass is tembaga. This is gangsa in Malay, gangsa. So bronze is basically copper, and usually they add with tin, and sometimes they add with the aluminium, and then sometimes they add with the silicon, and also sometimes nickel. Okay, so this thing is the major part. Okay, it's not like you, in order to make brass, it's not like you add 50% copper to 50% zinc. No, the base material is copper. You add just only a very few amount of zinc or whatever addition of impurities there. This you add very little amount. Very little amount. So this is what we call base metal lah. Base metal. Okay. See? So alloy is not like you add 50%, 50% plus 50%. No, it's more often than not, it's that they are like a base metal which make a bulk of the alloy, and then there are trace amount of whatever impurities they add. For example, brass, they add zinc into copper. Bronze, they add tin, tin, timah to copper. Okay, and sometimes they add also aluminium, silicon, and also the nickel. So that is brass and bronze, brass and bronze. So as you can see there, brass and bronze is a copper alloy. Because why? Because the base metal is copper. So that's why we call it brass and bronze under the copper alloy. Okay, let's see again here. And then we also have aluminium alloy. Okay, aluminium alloy. So you see at the bottom here. Okay, so this, you know, this is kitchen foil, right? Aluminium foil. In the kitchen, your mother, your father, or your family, even you have used this before, right? This is drink can lah. Okay, so this, even though the name is aluminium, okay, aluminium foil, this is not pure aluminium. When I said pure aluminium, it is sort of like 100% aluminium lah. This is not 100% aluminium here. Okay, it's not 100% aluminium. The aluminium is one of the most important lightweight alloy, and its production is only second to steel production. Okay, in terms of metal, the steel is produced a lot in terms of volume. The second most most common in terms of volume production of metal alloy is aluminium. The first one is steel. The second is aluminium. But when you want to make, like for example, when you want to make the aluminium foil here, this aluminium foil, and then when you want to make this drink can body, you don't just go to the factory and say, I want to buy this aluminium and make this thing. No, because aluminium alloy have different grades. Okay, let's talk about the grade of aluminium alloy. Okay, let's talk about some grade of aluminium alloy. So I put here aluminium alloy. Because aluminium, because aluminium you sort of like encounter it daily. I mean most of the day, many times in day. So that's why we a little bit focus on that. So aluminium, not all aluminium alloy are made same. Normally, when you want to buy aluminium, okay, you need to specify what type of aluminium alloy that you want to buy. Normally, okay, before we go to the grade, normally the aluminium alloy can be produced either casting or wrought. Okay, so casting is the process of you molten the aluminium, molten the metal, and pour into mold. So that is casting. The word casting and wrought, this term is normally you encounter it often when you talk about metal alloy. Okay, not only for aluminium, but any metal alloy, sometimes you will heard this term, casting or wrought. Okay, casting is basically you able to melt the metal and then you pour that the molten thing into a mold, and then you get the shape lah. Wrought is not. Is different. Wrought is heat treated or tool. So for example, has been heated. So it's basically the what we call. It's either has been treated. Let me put. It's either it's basically alloy that has been treated. And then work using tool. Okay, to give you the idea what's the difference between casting and wrought, let's go to the Google, our friend Google. So let's go here, and that's wrought. Let's say casting metal in mold. Okay, so basically this, yeah, you can see this thing. Okay, so basically you can melt the metal and then you put into the mold, whatever shape, and then you put the mold, and then you get, and then when it's solidified, you get cool and solidify, you get the whatever metal that assume the shape of the mold lah. So that is casting. Okay, so this is casting. When you say wrought, iron hammer, apa ni? Hammering. Okay, so this example of let me put here. Okay, so for example, if you see the blacksmiths, they don't melt the what we call the metal. This they use hammering. They call it hammering. They use tool and also heat. Okay, so this concept we call it wrought. WROUGHT. This is wrought alloy lah. So it's not molten, but it gets shaped by continuous hammering and also heating lah. So that is basically wrought. So the term wrought and casting, that's the idea lah, the difference between wrought and casting. Okay, so example lah. So not all aluminum alloy is same lah. So for example, let's say I talk about wrought alloy. So example, aluminium grade. Let's say I want to just talk about wrought aluminium only. Wrought alloy, meaning that the alloy, the aluminium that have been worked, not casting. So for example, when you try to buy aluminium in the factory, they ask you what is the grade, what is the grade or specification that you want. So normally aluminium grade can be divided into 7 to 8 grade. So there are 1000. Let me put in the black. So there are 1000 series. There are 2000 series. There are 3000 series. There are 4000 series. There are 5000 series. There are 6000 series. There are 7000 series, and then there are 8000 series. Okay, when I said series here, what does it mean here? For example, let's say I put aluminium. Let's say I just Google. Okay, let's say I just go to Google and then I type aluminium, and then I put 3003, or let's say 4 lah, 3004. Okay, so you see that 3004 aluminium alloy. Okay, so they are like code for aluminium alloy. So this code 3000, code 3000. Okay, so let's read a little bit. 3004 aluminium alloy. What does it mean? 3004 aluminium alloy is alloy in the wrought aluminium manganese, meaning that they add manganese. Okay, so this thing 3000 here, we know that they add manganese. They add the plus manganese. Manganese. This is manganese, not magnesium. Manganese. Okay, 1000 series is pure. It's pure, meaning that, but it's not 100%. It's basically mostly more than 90. What we call more than 99%. 99% aluminium lah. Aluminium. Okay, so this is basically they have the properties best corrosion resistant, and also what we call they are among best corrosion resistant among all grade, and also what else with this thing, they are have extreme ductility. But the problem with this 100 series is that they are lower in strength. Example for this is basically let me put in this color. Example is basically aluminium 1050. This is normally used for like aluminium foil lah. Aluminium foil. Okay, so you can see 1000 series of aluminium alloy is basically we can say a pure aluminium lah, more or less pure aluminium, because it contains more than 99% aluminium. And the properties of this 1000 series is that have best corrosion resistance among all the grade, 1000 until 8000. It have extreme ductility, but the problem with this 1000 series is low in strength. So example is your kitchen foil, kitchen aluminum foil, that is 1050. Okay, and then 2000, this 2000 is basically the add copper, this add copper, and then we learned before 3000 series manganese. This is basically the properties that for this is that they can be ductile, and also can be formed, and then example for that, example is that body of drink can. So you can see the body, the drink can that the aluminum beverage can. This is not the body. This is not beautiful picture. Okay, so that example of what we call a 3000 series. So I can show here lah. So this thing. Okay, so this what you see here, the body of aluminum can here is basically made from 3000 series aluminum alloy. This aluminum foil is made from 1000 series aluminum alloy. So you can see not all aluminum alloy is the same, because here they don't add anything. But of course there are some impurities. That's why we don't call it pure aluminum. But it at least 99% pure lah, have pure aluminum. It has 99% aluminum, but the rest is some impurities during the extraction lah. This is not the same because they add manganese, manganese. They add manganese to the aluminium in order to make it more ductile and more stronger in some way. And that's example is aluminium 3004, which is made for the body of the aluminium can lah. Okay, so now, so that's 3000 series. The 4000 series they add silicon, and then the what we call the 5000 series they add magnesium. Example for this, so this, when they add magnesium, they sort of like give the properties of excellent corrosion, excellent corrosion properties. Let me put in the black lah. Excellent corrosion. The properties, they provide excellent corrosion properties. And because of this, you often see this 5000 series aluminum is used in making like a vessel, marine vessel, because you know when you are in the sea water, the sea can sort of like eat the metal and so on. So this usually people call 5000 series as the marine series, for the what you call marine vessel and so on lah. And also, if for example, let's say aluminium 518382, this example lah, this is basically the top of drink can. What I mean here, if you look at this, the body here, this is the body, the body here is made from aluminium 3000, but the top here, the top here is a little bit different aluminium. It's not the same aluminium as this. Okay, the top here is made from 5000 series. Okay, so you can see, even though you see this drink can is just a simple can, but there are a lot inside in terms of material. The body is different than the cap, not the cap, I mean the top of the can here, this peeling off it is made from, normally it's made from the what we call 5000 series. The body is 3000. This is 1000. The aluminum foil is 1000. So you can see different alloy have a different properties lah, because depending on what impurities that you put. Okay, so 6000 series, you add basically the silicon and magnesium. You add basically you add silicon, and also you add magnesium. And this 7000 series, you add zinc. Okay, the properties of 7000 series is that it has very high strength, And normally example the usage for 7000 series is the aerospace lah. Aerospace, the kapal terbang apa? Aeroplane. The aeroplane body lah. Okay. So you see the aeroplane body, the aluminum alloy that make the aeroplane body is not the same as the aluminum alloy that make the drink can. So the aeroplane body, the aerospace, for the aerospace or require a very high strength application. Normally they use 7000 series, and 8000 series is basically the miscellaneous lah, plus others lah, maybe the specialty alloy, whatever. So what I want to say here is that the aluminium, even though same aluminium, but when you make alloy, you can make a different different type of aluminium alloys. So in this case, you have 1000 until 8000. Okay, so this is example of aluminium grade for wrought alloy. We don't talk about casting, okay. Casting is another thing, so I don't want to talk about that lah. So this aluminium alloy, at least now, because you encounter aluminium most of the time, so that's why you should know. I mean, aluminium alloy is not all the same. Also, this is copper alloy. This one we put in copper alloy. This is copper alloy. Copper alloy. Okay. So you see here, we just discussed about copper and aluminium alloy, meaning that copper become the base and also aluminium become the base. But you can make the base of any metal. You can make titanium alloys, whatever alloys, magnesium alloy, and so on. But for the sake of this class, I just focus on two only lah, copper and aluminium alloys only lah. Okay. So now, if you look at this, what we call at this image here. Let me put this this little kit down first. Okay, so much easier now to do. Okay, so now that is non-ferrous. What we do? Okay, so basically what we learned just now is basically non-ferrous. Non-ferrous is anything that don't contain iron don't contain iron inside the alloy lah. Okay, so now we have ferrous. Ferrous is basically you have like ferrum as a base metal lah. Here ada non-ferrous is alloy that not based with iron. Ferrous is alloy that based from the iron. So example for the ferrous alloy is cast iron and steel. The two most common ferrous alloy is cast iron and steel. Cast iron, example of cast iron is this, the one that is sort of like the frying pan, the heavy duty frying pan, not the lighter aluminium one, but this is the heavy duty, the one that is very heavy. So that example of cast iron. Remember the word cast, what does it mean cast? Is basically you can melt the iron and then you can pour into the mold. Okay, so the mold here in this case they are in the shape of the pan, so you get the pan lah. So cast iron. And so example of cast iron also this a gym plate, the weighing plate for the gym. So that's also made from the cast iron. Okay, and then another category for the ferrous alloy is steel. So steel is besi lah. The steel is basically this, and this is stainless steel. So let's talk a little bit about the cast iron and also what we call the steel here. Okay, so let me bring here. Okay, so we talk about the copper alloy, aluminum alloy. Now we want to talk about ferrous alloy. Ferrous alloy. So we want to talk first about the cast iron. About the cast iron. So cast iron is basically, what does it mean by cast iron? Is basically you have ferrum plus carbon. Okay, ferrous alloy here, this thing. Ferrous alloy is basically ferrum plus carbon. Okay, so that is basically ferrous alloy. They use carbon as the impurities. Okay, so cast iron is ferrous plus. So I think much easier I do like this lah. Much easy. So let's say you have this the timeline, and then let's say this 0%. So let's say this is carbon percentage, weight percentage 0%, and then let's say this is what we call this is 2.14. Let let me put here 2.14%. Okay, whatever above this, okay, whatever above this, okay, because ferrous alloy is basically iron plus carbon. So if the carbon content is above 2.14%, normally we categorize it as a cast iron, cast iron. Okay. If the carbon, so let's say, I will put it 1%, 1% here is a percent. So if the amount of carbon is less than 1%, let me put like this lah. Okay, if the carbon is less than 1%, we call this as a steel. Okay, so that is basically the difference between steel and cast iron. Okay, so for the cast iron, you have what we call around 2.5% of what we call of carbon content inside the ferrum, whereas for this thing is basically this carbon content. You remember here, this carbon content. Imagine there are unit ferrum plus the carbon. If the carbon content is less than 1%, we call it steel. If the carbon content is above 2% like that, we call it cast steel lah. But in practice, normally cast iron, the amount of carbon is between 3 to 4.5% lah in practice. Okay, for steel, okay. So the properties of the cast iron here is brittle. The property is brittle. This is one of the bad thing about cast iron lah. It's brittle. It's easy to break compared to the steel. But in terms of the goodness of the cast iron, is the cheapest to manufacture, and also sort of like it have easy to cast, and also they have what we call, they have excellent damping properties. What does it mean by excellent damping properties? Is that normally when you buy let's say you use a heavy instrument, normally at the base you need to put sort of like some base at the base of the heavy instrument. You need to put something to absorb the vibration. Okay, let's say you are living in the what we call in the flat, and then you are in the fifth floor. If you are buying for example treadmill, and then you try to exercise inside your house, sometimes those at the bottom, those below you will hear you are what we call you doing the exercise. So damping meaning that you put something below the treadmill or whatever equipment to allow the vibration to be sort of like absorbed. Okay, so normally we use this cast iron as a damper for heavy instrument. Okay, because you don't want vibration of the floor, vibration of the earth damage the instrument. That's why you use a damper. So that is basically one of the one of the advantage of the cast iron. It's cheapest, easy to cast, and also excellent damping properties. But the problem is brittle lah. It's not as ductile as steel. So steel lah. So when we talk about steel lah, so you can divide this further. So if let's say you have what we call 0.25 here in this region, let's say I put what color black lah. In this region, okay, we call this below 0.25%, we call it as a low carbon steel lah. Low carbon steel. In other words, we call it mild steel lah, Okay, mild steel. So between 0.25 to 0.6 to 0.6%. Okay, here let me put like this. It's difficult. Between this what we call the medium steel, medium carbon steel, carbon steel. Okay, and then the rest here. So this one, let me put here. So this one, let me remove this thing. We call it high carbon steel. High carbon steel. Okay, the more you add, the carbon percentage, the less ductile. Let's say this ductile. When you add more carbon percentage, then it become less ductile. Okay, low carbon steel, the advantage for this is basically high ductility ductility. So it's easy to form. Example for this is basically automotive car body, let me put in the different color. Example for this, they use for car body like that. Okay, so that is basically the low carbon steel. They use low carbon steel. Medium carbon steel ni they have better ductility not better ductility, less ductile, but it's stronger. Okay, so I can put here also this thing ductile. Let me put here. This is ductile, less strong, and then less ductile but strong. Okay, so example for what we call for this medium steel is basically railways track. Okay, jalan kereta api tu, the railways track tu, the train railways. So that's, you see that the method, the steel is a little bit different. It's more strong there. High carbon steel is basically very is very strong and normally they use it for the tools, for the tools making, for the what we call hardest. It's the hardest. So normally so this is the hardest, but sacrifice ductility. Hardest. Because it's hardest, normally they use this high carbon steel to make like what we call the tool. They use a tool and die. They use for tool and die. Tools and die. Okay. So for example, let's say tool. So let's say this thing tool. So let's say I put here tool die, tool steel. Okay, tool steel. So you can see this thing, spanner, everything here. They are using this spanner and so on. They are using what we call the high carbon. Okay, around more than what we call 0.6 to 1 to 2% above 0.6 above 0.6, but basically it's above 2.6 but around 1% Okay, so that's tools. So they use tools so that it doesn't wear because if something hard, when you do it repeatedly, for example, you have a spanner and then you want to open the screw or bolt, you do it repeatedly. If the spanner mouth is ductile, then it will sort of like deform. So you need something hard. So that's why they add more carbon to this iron to make it more harder alloy So that is basically the high carbon steel and so on. So if you look here, there are also some class, we call it stainless steel. This stainless steel. Okay, let me talk about stainless steel a little bit. Okay, so stainless steel is basically normally they use here. Wait. Okay, so we have stainless steel here. Stainless steel is basically they can use either low carbon steel, medium carbon steel, or high carbon steel. They can make it stainless steel by at least 11% chromium. Okay, so that's how to make what I call stainless steel. At least 1%, 11% chromium. So you put chromium inside along with the ferrum and also the carbon. You add also chromium. So the reason for this, if let's say you have, for example, the steel, the normal steel, let's say this steel, okay, so you know there are like oxygen outside, okay, the oxygen will sort of like attack the steel surface, and then the steel, the what we call the iron inside the steel will make what we call iron oxide, okay, iron oxide. So this is basically rust. So that's why steel, if you don't make stainless, it will rust, because the steel, the iron inside the steel will react with the oxygen in the atmosphere. The reaction will create iron oxide, and iron oxide is a rust. Okay, so when you add chromium, let's say here you add steel and then you plus chromium, what will happen? The oxygen here, the oxygen, let's say the oxygen here, the same thing will happen. The oxygen will react with what we call thing inside the thing, but it will react with chromium. So it will react with chromium, and it will create chromium oxide. The difference between chromium oxide and iron oxide, chromium oxide is transparent. Chromium oxide here is transparent. So basically you got sort of like a transparent layer on top of this, which is a chromium oxide, which is this a layer of chromium oxide that sort of like prevent the air, the oxygen to go into and sort of like attack the ferrum, so you don't get iron oxide lah. So this is how the stainless steel work. The chromium create a sort of like passive layer on top of the material, the steel, to prevent further attack from the oxygen. So the oxygen cannot bind with the what we call with the iron. So there are no iron oxide, no rust lah. So that is the how the chromium oxide was made. Okay, the last. We talk about the steel and so on. So we talk about the what we call. We talk about the metal alloy, dislocation, copper alloy, aluminium alloy, and then we also talk about the ferrum alloy, and then we talk about steel, cast iron. Now, before we end this thing, we need to ask how they make this steel. I mean, because the most common metal that is produced in the world is steel. So this is the most common material when we talk. Okay. So when we talk about what we call the most common metal that is used in engineering is steel lah, because steel is produced a lot. So we need to ask a little bit how steel is produced. So let's see this thing. Okay. So making steel. So normally when you want to make a steel, you need to start with the iron ore, because steel, the iron doesn't exist in a pure form. Normally iron in the real life, in the nature, they will exist together with the oxide, with the other stuff. Okay, it's rarely iron they sort of like they exist as a pure form. Okay, they always sort of like make the connection with other stuff. So this iron ore. Okay, so you can see the rusty color there. So that is basically iron oxide. So this iron ore is mined from the quarry lah. Okay, so they start with this, and then they add with the coke. Coke is basically charcoal, arang. Okay, coke here is charcoal. Okay, so basically what they want to do is that they want to sort of like melt this thing to get the iron. They want to melt the iron. They call that thing is smelting. Give me 5 minutes. They call this smelting. Smelting. Smelting is basically the act of what we call process of heating. Process of heating metal ore. Heating. Jap. Hai. Aduh. Bang. Sana. Process of heating ore. Alamak. Process heating ore to extract base metal lah. Base metal. Alamak. Base metal. So okay, dulu. Okay, so that is smelting. The word smelting mean that. Okay, so the idea is that you have this iron ore, meaning that they have a rock. Ore is basically the rock or sediment contain a mineral. So here inside this ore, they are iron. They are iron. So basically, in order to take the iron, you need to liquefy the iron to melt the iron. Okay, in order to melt the iron, you need fire. Okay, in order to create fire, you need to use a fuel. So the fuel is a charcoal, arang. Coke here is basically a charcoal that has been burned. So there is like a better version of coal lah. Coke here, COKE, is basically the better version of the arang or charcoal lah. So basically it's just like a fuel lah. So you combine this together, you put in the furnace. Okay, you put in the furnace. So basically this when this happen, you sort of like mula kejap. Salah macam ni. Ayo. So you have this blast furnace. So basically this blast furnace is basically what happened there is basically you are using coke as a fuel to melt the iron inside the ore. So that's why it's fire there. Okay. So how blast furnace work is that they blast the air at the bottom, and then you get heat, and then the iron will melt lah. And then once you get the melted melted iron, you get this melted iron lah, melted iron. Okay, the thing is that in this molten iron, if you look, one thing that's important that you should know is that if I draw here iron, carbon, sekejaplah, carbon phase diagram. Ayo, tunggu nanti. Mana nak ambil ni? Okay, let's say this lah. I don't know whether you can see or not. I hope you can see. Okay. Macam ni. Tak ada susah macam ni. Okay. So this is phase diagram of iron carbon phase diagram. What happen when iron? Kenapa? Ini bos. Kena nangis ni. Okay, so for example, nak belajar lah sekali. Okay, so for example, let's say this is a carbon, and if you look here, this carbon, iron carbon phase diagram, you don't need to know a detail lah. But I just want to show here, for example, this carbon percentage, and then this is temperature. The y-axis temperature, the x-axis is the carbon. So if you look here, 4.727% here, this is basically 4.27% of the carbon added to the iron. Okay, so if you look here at this point, you can see the temperature going down, right? Temperature going down. So meaning that what does it mean is that at this moment here, when it's molten here, they are iron inside. Okay, because not iron, the carbon inside. Salah bos. Sini ni. Okay, they are still sort of like molten. They are still they are still carbon inside. They are still carbon inside. That's the reason they will be they can be melted, because when you have, where is the carbon coming from? The carbon coming from the coke. Because the idea is that to make a steel, you need to add iron. Because here when you extract, you get iron only. There are no carbon. There are some impurities, but carbon, maybe there are trace carbon lah. But when you add iron and coke as a fuel, the carbon inside the coke will go into the iron. So the carbon there inside the coke not only help to fuel the not only help to fuel the furnace, but also to reduce the melting point of the iron, as you can see from the what we call from this phase diagram. When the so for example here, when the what we call when the amount of the carbon is around 4%, it will lower down the melting point of the iron. Okay, so the coke that they use as a fuel also act as a what we call melting point, to lower the melting point of the iron, so that you can melt the iron at lower temperature lah, at lower temperature. So to show that this thing, there are still carbon inside that. There's still carbon inside that, but the carbon here is around 4%, around 4%. So that's 4% is more or less in cast iron region lah. So you get this thing when you get molten iron, you get this iron peak. Iron peak is basically the iron with some carbon. Okay, carbon that's happened during the molten iron part here, because we said before the 4% carbon there that lower the melting point of the iron, make this thing possible. But this thing, the liquid iron here still have carbon. So that's why iron peak, meaning that the iron plus carbon, but that carbon is around 4% like that. So we don't want that, because that is cast iron. So what they do, they are basically how they make it remove the iron is using the what we call a Bessemer process. So they use iron peak, they put into another, they put back into the blast furnace, but they call it a converter lah. It's the same idea, but now they put the pig iron, they don't put the coke. Okay, because remember inside the pig iron there are already a carbon inside the pig iron, so they use that carbon inside the pig iron as a what we call as a fuel, as a fuel itself. So so now the Bessemer converter is basically they put the iron peak inside the Bessemer that stuff, the Bessemer converter, and then they blast the air at the bottom. Okay, the same idea with the blast furnace, but the difference is that in the blast furnace, the top one here, the difference here is that they add coke. They use coke plus iron. But in this Bessemer converter here, they don't use coke. They just use iron peak, because inside iron peak there are already carbon. So they use carbon inside the iron peak in order to sort of like to create a fuel to melt this thing. So that is we call it Bessemer converter lah. So so nowadays they use instead of using air, they use oxygen. During the early days, they use air only, because they cannot have a pure oxygen. Normally when you want to make fire, you want to use oxygen. When you use air they are oxygen, but they are not pure lah. So the temperature that you can get when you use air is lower lah. So the Bessemer converter, they use air, they blow air at the bottom to melt the iron peak. Okay, they melt the iron peak. But modern day, because the oxygen, the liquid oxygen is already available, there are a lot more not liquid oxygen, the oxygen gas is available in pure form, in mass. So they basically, instead of blowing the air, they blowing the oxygen gas. Much easier lah, much faster temperature. So when you try to do this, when you try from iron peak, you blast, you put into the Bessemer converter or basic oxygen furnace, what you get is basically the iron without any carbon lah. Because remember, the carbon inside the iron peak is used as a fuel itself. So the reaction happen, the carbon will be removed lah. Okay? So you get the what we call the iron. So you get the iron. Okay, so you get the iron without carbon at all. So now it's much easier for you to add 1% or 0.6% later. Okay, so the idea of Bessemer converter, the idea of this Bessemer converter is that they remove the entire carbon first inside the iron, and then only then they add the carbon later. Okay, and then you use a continuous casting, and then you get steel, billet and slab, and then you can use it as a steel lah. Okay, normally from here the iron pick from here okay, from the iron pick, remember inside the iron pick there are 4% 4% carbon. Normally the way how people remove the carbon, remember the blacksmiths, they hit the whatever metal, and then they hammer it. So the hammering part here is basically the purpose of this hammering part is to remove the carbon. One of the ideas is to remove the carbon lah. So that's why when the blacksmiths hammer the thing, they remove the carbon impurities. So from 4% it can be like 2%, 3%, 1% and get good steel lah. But the problem with that, you need to hammer it individually. That's why the Bessemer process here, they instead of hammering the iron pick, they just put into the Bessemer converter, and then they blast with the oxygen or air, so that it removes the entire carbon, and then they add carbon later on. Okay, so I hope this enough for the metal.